So my talk is going to be a big data streaming recipe, and I want to show you like what you would have to consider if you want to build a streaming real-time application on your own. So the first question you might want to have is, why would I call it a recipe? And the idea is that I'll show you a couple of ingredients like frameworks, tools, and different concepts, and what I've worked with so far and what my experiences were. And then you can decide what's important of that really and how much you want to add, or if you want to leave something out, or if you want to add some other things. So the idea is that you'll go out here and have to learn some concepts about these different frameworks that are, like everybody talks about them, big data and all these things. Exactly. So who's that guy who's talking to you? I'm a software developer from Munich, the place where the Oktoberfest is. Some of you might have heard about this. And I work for T&G Technology Consulting. So it's a small 300 people company in Munich, but I'm at a big client in the telecommunication business. And what we do is we build some real-time applications where we process mobile phone events. So customers of this company, when they use their cell phone, every time they use it, like they place a call or do a text message, an event is sent to us. Okay, so we're talking about 5 billion events per day. And these are data records that contain like the location where this happened and some other things. And what we do is we're kind of working on a trade-off here, because on the one side we want to have useful statistical insights, of course. That's what the other companies pay them from then. But on the other hand, we have a big focus on privacy and anonymity of the people. So in general, what the use case is, for example, if Bayern Munich is playing, then we could tell people how many in the stadium were actually from Munich and how many came from somewhere else. And while we want to have a high level of data quality, on the same time we want to have a lot of encryption, a lot of anonymity. And so the laws in Germany are pretty strict about data privacy, and people from this governmental agency actually come to us and do code reviews and really look at all these details where the stuff is encrypted and anonymized. So this is what we do, just so you know what I'm doing. And so coming back to this recipe, if you guys are ready, I'd say, let's cook. The first ingredient I'm showing you is probably pretty obvious. It's hardware. Okay, if you want to process 5 billion records of data, you can't do that on this machine. So you need quite a lot of servers. And while this is obvious, there's some things you might want to consider. So if you handle a lot of data, you always want to replicate the data as well, because things will fail. We'll get to this also later. So when you think about how much hardware you need, you also always have to think about replication and redundancy. So everything should be there at least 2 or 3 times. So in case of failure, everything's still there. Also, the applications, maybe they have to remember things. So the state of the applications might become quite large. This is also a fact. And then, especially in our case, we have high load peaks. So you can imagine in the evening or in the nighttime, not many people use their phones. But like, especially during lunchtime, you know, when people have lunch at work, they text their families and all this stuff. So there's a lot of events coming in. And so you need to also have some kind of mechanism to be able to balance this. That sometimes there's less information, less data, and sometimes there's more. And then also, you will always want to spare some resources for extraordinary situations. Like there was a delivery crash of data, and the data of yesterday has to send in completely again, and then you have to process this while the normal application is running. So this just for completeness, the hardware. If you want to build something, really calculate all these things. So take that into account. Okay. What we really need now to process data is a stream processor. So like a framework that is able to handle huge amounts of data. Because if you just do it, you know, just write public static void main, yeah, that's not going to work. You have to think about some frameworks that you can use there. And there's a lot of frameworks actually. And new ones keep popping up, and old ones, nobody talks about them really anymore. And it's difficult to decide what you want to use, yeah? And each of them has its own benefits and also disadvantages. So what I can tell you here only is you have to really analyze what you need, what kind of features you need, and what's really important for your application. And I want to show you three stream processors here, which are Storm, Flink, and Spark. Spark streaming, because in my opinion, they're the 3 top-notch stream processors. There's others like Samza and Trident, Heron, but I want to focus on these three. If you want to build an application yourself, then after this you probably know a little bit about what you should look for, and then you can decide on your own. So just to show you how important this topic is at the moment, so you see these graphs from Flink, Storm, and Spark. They're definitely increasing. Storm is going down a little bit, but in my opinion, they've worked a lot in the past year to come back up. So I think they might also do the turn for the better as well. And just a note, I just Googled for Spark streaming here and not Apache Spark, because Apache Spark is also a huge batch framework. Okay, so getting down to business, what is the functionality that we're actually looking for? And in general, all of these stream processors provide you with a couple of functions like map functions, windowing, aggregates. So a map would be something comes in, gets transformed, and gets pushed out. Or a flat map would be something gets in, and maybe multiple come out, or nothing comes out. Windowing is also very important, that you want to take a look at data, for example, in time intervals. Like you want to look at them for 10 seconds, and then another 10 seconds, then another 10 seconds. These would be tumbling windows. What you could also have is sliding windows, meaning looking at these 10 seconds, looking at these 10 seconds, these 10 seconds, and so forth. And aggregates, you want to sum up things and count them and whatnot. And these are all provided, basically, by all these frameworks. And then you have some specific functionality like machine learning. We just saw that Spark is very strong in machine learning. Another important thing is graph processing. You know, graphs of the social networks that keep growing and growing. It's not a static graph anymore, it's a developing graph. So there's also frameworks that have nice libraries for this. So let's look into these frameworks. So for example, Flink, which is like the newcomer, so to say. Flink's originally from Berlin, from my home university actually. Funny thing is they came to a conference at our company, and then I realized I know this guy. And we went to class together, but we didn't know. It's written in Java and Scala, and what Flink does, it processes records one at a time. Not all frameworks do that, but Flink does. So one record at a time is processed. And you can use Flink in Java and Scala. There's also some Python out there, but that's only like experimental. And what Flink also is working on at the moment is queryable state. So that means the current state of records, like all the information there is, you can query it in real time. But this is not yet stable, it's a new thing. Maybe I'll talk a little bit about that later. So how does a Flink application look like? Pretty much like this. So it's not so much code, and what we do here is I call this Hello Twitter, because I download all the Twitter data, or I stream it, and then I count from where do these tweets come, and which language are they written. So we start with having some execution environment. The execution environment is something that like takes care of how everything is distributed and how parallel it is and everything. It's more of an abstract thing right now, but you need this to start. And then what you do is you add a source to your environment. And in this case, you add a Twitter source, which connects to Twitter as I'm speaking. What you get are a couple of tweets. They're just strings, and these strings are JSONs. And now what happens is you do a flat map. So a flat map means I take a tweet that comes in, and I process it, and I give it to the next operator. So in this case, all I'm doing is I get the language of the tweet. I hope you can read this. So there's a tuple 2 that I'm putting out. I get the string language of our tweet, and I add a 1 in the end. So I get a tweet, and I send language, comma 1. So like German, comma 1, or Romanian, comma 1. And I do a flat map here because there could be parsing issues, so I could have an exception. A map would be when one thing comes in and one thing comes out. I have a flat map here because it could be that there's an exception, and so nothing gets put out. Okay, now I have these tuples of language and 1, and then I key this by the first part of the tuple, which is the language. So it means Flink collects or sees, okay, this is a German language. I push it to this operator, or to this server. Yeah, it's Romanian to this one, another Romanian to this one, another German to this one, and so on. And then it's keyed. And then I take 10 seconds time windows, and I sum up the second value of the tuples, all the ones. And that means that I'm counting up all the ones, and then I know how many tweets there are. And so, just that you believe me that this actually works. Oops, that did not work. Wait, where is it? Wait. Why is it not going over there? Are you seeing anything? No. Ah, something's coming. Sorry about that. This is really awkward. Are you seeing anything? Okay, so yeah, I have to improvise here now a little bit. Where's the mouse? There. This is all the code that I just showed you. Let me run this. So this is connecting to Twitter if the internet connection is working. So something is created here. And there you see, okay, we have 15 English tweets in the past couple of seconds. Now if we wait 10 seconds, the next windowed stream gets put out. So let's just wait for 10 seconds. Okay, yeah, so this is downloading the Twitter data in real time and then putting it out. Of course, we have some latency here because I did 10 seconds windows. It wouldn't be possible to just print it out because if I sum the tweets up, I need to have some sort of aggregation and latency. Okay. Let's go on. Don't need this anymore. Okay. So this is Flink. What about Storm? Storm is in some ways similar to Flink. It was made at Twitter. It's written in Clojure and Java. And Storm also processes records one at a time. Okay? So also one record comes in, it gets transformed, and it gets pushed away. And Storm, the nice thing is you can use it with any language, so you don't necessarily have to use Java or Scala. And Storm is also doing something like Storm SQL, which they're providing. And Storm looks a little bit different. So Storm starts with a topology, and this is like the environment in Flink, so to say. And what you add here is a spout. Spout is just the Storm word for source. Just reads the data. It's the same thing over and over again. So I just read the Twitter spout, read the Twitter data. The one in the end just means the parallelism on the spout. And then instead of using flat maps or map function, you have bolts in Storm. And each bolt is like an entity that processes data. And it usually does a little bit more than just a map. And here I can create a new Twitter language count bolt, which I wrote. And then I can also call this with tumbling windows, again with 10 seconds. And I do a fields grouping, which would be the same thing like a keying in Flink. So this is part 1 of 2. The main work gets done in these bolts. So you always have to write a bolt that does the stuff. And here's a little bit of different concept, because we have this bolt and we have to extend some function that's provided by Storm, and we have to override, we have to override an execute function. And in this bolt, we have a hash map from string to integer with the counts of languages. And what I basically do in this bolt, I override this execute method. This already gives me some sort of tuple window, which is a list of tuples containing these tweets. And then I also extract the language, but instead of emitting these tuples of language, comma 1, I just update this hash map. Okay, so every tweet comes in and I update the count in the hash map. And what I do then, I emit all of these values in the hash map. So all these tuples, Romanian, comma 18, English, comma 15, and so on. Okay, and what you also have to do is you have to declare what the output fields are so that the next operator knows what you're doing. Okay, last framework I want to show you is Spark. Spark Streaming, which is from Berkeley, written in Scala. And Spark is a lot different because it's doing stuff in micro batches. So Spark, maybe you've been here in the previous talks, is actually a batch program. And they invented Spark Streaming, which just uses their batch framework to operate on unbounded streaming data. But it's still doing batches as opposed to Flink and Storm. And they also do some SQL on streams. I just wanted to show you that they're all kind of going in the same direction. And so, yeah. And Hello Twitter and Sparks looks quite similar. You also have some stream in the beginning of tweets, and then you have a map function that maps your tweet to the language. You have a window function, you count by value, and so on. Okay, but although this looks quite similar, it's a lot different because it's doing micro batches. Okay, so now you kind of know how these frameworks look and how you have to implement your algorithms with them. And your application would look somewhat like this. You have Twitter data coming in, And then you have some sort of graph with operators. They could be bolts in Storm, or they could be map functions or flat map function or whatnot. And of course, these operators operate in parallel. So you have 10 servers, and then they're spread out there and doing all the work in parallel. And what you always have is some sort of master. I put this in quotation marks because depending on the framework, they have a different name. They could be a Nimbus, a master, or a job manager. But there's something there, some server, or some process that is distributing the data to the correct entities. So like in the keying example, there's someone who keys the data and brings it to the right operator, that the right operator gets all the Romanian tweets, for example. Okay, this is how it looks like now. What you want to add then is some real sources in sync. Because what you don't want to do is you don't want to get the data from Twitter directly. Because if your application crashes, and it will crash a bunch of times, you can't like call Twitter and say, hey, can you send us these tweets again from last hour? We had some downtimes. Probably not going to happen. So you want to have some sources, some persistent sources, which would be Kafka. We'll get to Kafka in a little bit as well. You could also read from HDFS, which is a distributed file system. So again, it's like a file system, but you want to have everything replicated. So it's a file system where the data is spread on many, many different nodes. And then there's one name node that you ask, hey, please give me that file, and then it gives it to you from some server, but it's always replicated. Big data also always has to do with databases, and with cloud more and more evolving with S3 storage. And this is already provided, most of this, but sometimes you have to build your own sinks and sources, but this is usually easy. But so what is to consider when you add sources and sinks? One is fault tolerance, the Twitter example that I just gave you. What you don't want to do is read the data direct from Twitter, but what you want to do is you want to have a source, a persistent source in between. So you want to have some simple application that gets the data from Twitter and then writes it to some persistent source, that it's stored safely somewhere. And then your application can read from that source. And the idea is when your application crashes, you can restart it and can read the stuff again because it's persistent. Of course, you're only mitigating the problem to the first application that's reading from Twitter into your source. But the idea is that you can that's quite simple, just read data and put it somewhere, as opposed to having this huge application that's doing machine learning and all these things. We'll get to this also in a later point. But the idea is have some persistence before your application. Something else would be data quality. If things crash, they can be sent to the next operator multiple times. And depending on the use case, that's unimportant or that's bad. If you think about a bank, the bank can't really tell you, well, all these transactions, all these wirings of money have done at least one time, maybe more. That's not good. In some cases, it doesn't matter. If it comes out 2 or 3 times, we don't care as long as it gets output sometime. And if you use a database, for example, this could be a very convenient way, because if things are written into the database 3 times, it doesn't matter because it will just overwrite the value and the stuff is correct that comes out, no matter if this writing to the database is done 3 or 4 times. Another thing that's nice is a decoupling of modules. So you don't want to have this huge monolith that does all the work, but nice would be if you have smaller modules that do certain steps and then write it somewhere else and then the next application picks up. This is especially if you have a bug in one application or you want to upgrade this one application, it's nice because then you don't have to update everything, but you can just have to update this one little part and just have to deploy one little component. Another part is, of course, also latency. Depending on what sources and sinks you need, data can be made more or less quickly available. We'll get to this also in a second. So now our application looks kind of like this. We have something that gets the Twitter data into some persistent source. We have our application, and then we write it somewhere, either a database or some other source for the next application. And now we really get into details about how we process data. And one of the most important things there is stateful operations. Yeah, stateful operations, what does that actually mean? Well, here's the difference between stateful and stateless. A stateless operation would just be tweet comes in and I emit language, (1). I don't care what happened before, I don't care what happened after that. I just emit this right away. Or what we do most of the time is record encryption. In record encryption, something comes in, you encrypt it, you send it back out. So there's no sort of state, no memory of this operator. A stateful operator, for example, would be the count. Because this depends on multiple things, not only on the current tweet, but also on the ones before and after that. Also, machine learning model is a very good example for stateful processing. Records are coming in, and you update your machine learning model on the fly. So this is also stateful. And why is that important, and how do we actually do this? Well, we could just store it in some variable in the operator, like we did in the storm bolt. In the storm bolt, what we had there was this hash map, as you recall, hash map with languages and counts. And each time a record came in, we looked at the language and we updated the value in the hash map. So this is state. But what you have to think about that you do everything in parallel, right? So the state is distributed on many machines. But if you think about it, the state is really an application whole thing, and not only the thing of one operator that's on this machine or the other one that's on that machine. So it's something like one total or global state, and so you kind of need to make sense of getting this all together sometimes. You could use a database as a state, for example, and we're going to get in more detail about this. But the question really is what the application does when it crashes. So you think about the hash map in the storm bolt, tweets are coming in, gets updated, and so there's like Romania 15, English 20, and then the application crashes. Well, how does the hash map look like? It's empty. And this is, of course, something you don't really want to have. And it's probably also something you don't really want to manage yourself. You don't want to use that state and save it somewhere, and then if everything crashes, you want to read it again. This should be provided automatically, and of course it is. So how does this look in Storm? We need to specifically add the state there, and we can't use these hash maps, because if things break, the state is just gone. But there's something like a key value state, which is backed by Redis. So what it does is you update this key value state, which is similar to a hash map, and it works the same way. I'll show it to you in a second. And then every n seconds, it just pushes this state to Redis. So if something breaks down, it can be just reread from Redis. Redis is a database that stores key values, for those of you who don't know. Exactly. So the state is buffered in memory, just in a hash map, and then periodically written to a database, but you don't have to take care of this. All you have to do is you have to make your bolt a little more a little better, so to say. And you need to extend a different kind of bolt. That's all you have to do. It's not a base windowed bolt, it's a base stateful windowed bolt now. And instead of a hash map, you have this key value state. And then you also need to implement your init state function, which is usually very easy. And then Storm does all the work for you. Okay, so it writes the stuff to Redis. When things break down, application comes back up, it reads the state from Redis, and you're good to go. How does this look in Flink, for example? In Flink, it's mostly out of the box already, so you don't have to worry about anything. So like the functions that I used, like sum and window or count, you don't have to do anything. The state is already in there, and it's already backed somewhere. It can be backed also to a database, which is RocksDB, or to HDFS, this distributed file system, or even to S3. So you mostly don't have to think about anything. The state in Flink is kept in memory, but if it grows too large, it gets spilled on disk. And this is a very important feature, because in Storm, if the state gets too big, it can't handle it anymore, because it will get out of memory exceptions. And Flink does not have this. If the state gets too large, it starts writing it to disk as well. And if you use your own function in Flink other than window and sum, and this is often necessary, or sometimes even if you do a very difficult stuff, so to say, and those functions that are provided are not enough anymore, you do have to think about state, and in Flink it's a little bit more difficult than in Storm, because you have to think about keyed state and operator state. And the difference here is, when you have these tweets or these languages, the stream is keyed based on the language. So all the Romanian tweets will end up on the same server, and all the English tweets will also end up on the same server. So these states are somewhat disjoint. You know, the Romanian tweet will never affect the English language tweet. So this is a keyed state. The other thing would be operator state, is when you read from some source, for example, and you have 10 operators that read from the same source, And of course, they have to somewhat talk to each other, because if operator number 1 already read the language, the tweets 1 to 10 or the messages 1 to 10, the next operator needs to know about this. And so then state handling is a little bit more difficult, because these operators have to kind of have state that is interdependent. And so there you need to do a little bit more, but it's similar to the storm example. You also have to implement some state functions, and that's it. It's basically very easy. In Spark, it's a little bit different, because in Spark, again, it's not not real streaming, so to say. It's micro batching, and so every n seconds, you have one new program. And what happens is the stuff gets read, and it's read as an RDD, which is a resilient distributed data set. So the whole data gets spread on all these workers, and all transformations are made on the whole data set. So whereas in Flink and Storm, operations are made on one record, in Spark, everything is made on this whole data set. And what Spark does, it saves the lineage. So something comes in, a data set, on second 0. It gets mapped and whatnot, and this is saved. It's saved what needs to be done to get the current state. So in case something breaks down, we reread the data set, so to say, because it will be replicated at first, so we still have it. And then the operators can be done again and again, and so we have state automatically, so to say. And of course, what can happen is that here you see one program in the first line, stuff gets read in, it gets transformed, and then after the batch is over, the next batch gets read. So that's the second line. And as you see from the arrow, the second program depends on the first program. And then also, of course, if the second batch fails, Spark has to remember what happened in the first batch, because the second batch is dependent on the first one. And if you think about a program that's running 24/7, these lineages, these dependency chains get longer and longer. And at some point, they're just too large. But what Spark does is it checkpoints these lineages so that it writes the stuff to a backend, and so that it doesn't have to remember anything. Because you can imagine after like 20 minutes or what, the first stuff is not important anymore. Maybe it's still in the batch we're actually currently computing, but it will save checkpoints in the meantime so that we can forget what was minutes ago. The state here in Spark can also be spilled to disk, so we don't have problems with out of memory, which is very important. Exactly. So this is what state means. What happens if you run an application 24/7, 365 days a year? Things will go wrong. And there will be very interesting failures that you can have. Yeah, I don't want to get into more details, but surprising things can happen if you do many, many things all the time. So you really have to care about failure tolerance. And what we need for failure tolerance, we already have, basically, because I already showed this to you. The one thing is that the state needs to be checkpointed to a backend. So these hash maps, are not hash maps anymore. They're a key value state, and they're written to Redis. So in case of a failure, we can reread the state. But so if we, for example, checkpoint every 10 seconds, or say every 1 minute, you can configure that. If you read the tweets, and then you do a checkpoint, and then things continue, new tweets are coming in, and after 50 seconds, the system crashes. Of course, you can reread the checkpoint, but then your application is 50 seconds behind. And what you need there is that you can rewind your source and can reread that data. You can't ask Twitter to give you the data again, but remember we have this persistent source between Twitter and our application, so you are able to rewind actually your source and reread those tweets that are lost on the way. So how does this look in Flink? Flink has several state backends. It's a file system, for example, or RocksDB or S3. And, well, what happens if the job crashes? Of course, we read the checkpointed state and we rewind the source. So let's look at this particular example here. So this Kafka source contains 5 records, and Kafka writes them in, these could be tweets, from left to right. And it's a FIFO thing, so our application reads from right to left. So at the current state, we have read those 2 yellow records. We have read them, and in our job, we counted them. We don't do anything else but count the records. Not very exciting, but that's what we do. And so here you see it has counted 2 records, and one of them is already pushed to the next application or pushed wherever. So now we continue, or now is when a checkpoint is written. Okay, so what we checkpoint is the reading point. Yeah, so in the case of a failure, we know until where we've read, and we checkpoint the number 2, which is the count that we currently have. So application goes on. We read 2 more records. We counted them, so the current state is 4. And we already emitted 3 of them. And now we imagine the application crashes. So what does that mean? We read again from the checkpoint. Checkpoint saying us the count is 2. And we should read again starting from that red record. Perfect. We read the red record again. Then we read this purple record again. The state was 2 at the checkpoint, so the state is 4 again. Does anyone see something fishy about this? Maybe. Yeah? Exactly. If we go back to the checkpoint now and we reread the red and the purple, the red one gets emitted twice. So we have the state is actually correct. The state is 4 when we read again from the checkpoint and then the red and the purple one. But the output is incorrect. Okay, so the state was counted exactly once, but the output actually isn't. And that's a very important thing to realize, that exactly once processing doesn't always mean that what comes out is still exactly once. And we'll get to this in a couple of minutes as well. Let's take a look quickly at how Storm does this. It's very similar as well. The job gets restarted and you read the state from checkpoint. And Storm has a different way of working with replaying the data. What Storm does is, if this is our application, the first operator reads the data from somewhere and it duplicates it and stores it in memory. And now it waits until, or it emits some record to the next operator. This one goes to the next operator and so on. And so you see this yellow record here that just passed the 3rd in line. The previous operators always tell the previous one, I'm done with this record. And the first one waits until it hears from the very last operator, I'm done with this record, and then it deletes it from the backup. And you configure a time that it waits. But so what can happen is, if it just takes too long for some reason, it can be emitted twice. Okay, so even if you have checkpointing and everything, and rewinding your source maybe, in Storm records can be internally duplicated. So you also don't have exactly one state. Because if this yellow record just takes too long, even if there's no failure, it could be emitted twice because the first one is getting nervous and saying, oh, I haven't heard back from all these operators, I'm just going to send it again. So then this is, of course, processed twice and the state is also incorrect. And so what you have to do in Storm is you have to implement this ecking, which is just saying, hey, I'm done with this record. We can continue. Quickly about Spark, we basically already covered this. It checkpoints the lineage of programs, so it checkpoints the first RDD and the transformations necessary. And so if it breaks the application, then we can just compute it again. And Spark has a very smart way of doing this, because if one batch fails and it has to be recomputed, of course we're already reading the next batch, so the old batch gets distributed quite smartly and produced in a quicker way such that we can keep up with the whole flow. And that one failure, if it happens, we can just compute it on the fly while the other rest is also computed. So now our application looks like this. We have a source, we have a sink, we get the Twitter data, we have this master that's distributing the data and the resources, and we checkpoint the state such that in case of a failure, we can come back to the state, rewind our source, and continue. So some people would say now the application is fault tolerant, but I think there were people, you might know them, that told about a very big application that was fault tolerant. You maybe know this. People said, well, this is unbreakable. There's just this one little hole. If you shoot in there, everything blew bad, and that's not going to happen. So what you need here is high availability, because this master here, if it crashes, then the whole checkpointing thing doesn't work anymore. because we don't know where we checkpointed and all this stuff. So we need high availability. What does that mean? What you don't want to have is these single points of failures, which are these masters. There's just one of them, and if he fails and he knows everything about the state, then the program is still down. And these masters, again, I put them in quotation marks. They could be job managers, Nimbus, or master, depending on the framework you use. And what you use for this is the Zookeeper framework, which is a distributed configuration service. And practically it looks like this. Then you have this master that's, bless you, the master that is distributing the work to the workers, and Zookeeper is taking care that the knowledge of the master gets spread to some other master as well. So there's always another master in the background. It doesn't do anything, but it's always there. And so in case this master fails, the other one can come up, and he knows everything already, so there's no loss at all. So now the second master is the one who's in charge, and the first one will be restarted and then also get the information from the now running master over Zookeeper. Yeah, and Zookeeper is replicated and distributed. So now the application looks like this. We have this master who does the checkpointing and Zookeeper who takes care that there's always somebody else who knows what to do in case of a failure. Okay, coming to the last ingredients here, flow control. That's a very important thing. And I want to show you this in here. Put the mouse here. This would be our application. Data is coming in and processed and whatnot. And what happens is the lower operator here, it's not fast enough. Maybe it has to do some encryption. Encryption takes very long as opposed to other things. So this is bad. 3 records come in and only 1 is coming out. So what's happening is that this is kind of blowing up, and memory is getting fuller and fuller with all these in-flight records, and at some point the application just crashes. Well, then you restart the application, and then the same thing happens again, right? So that's no good. So what this operator here has to do, whoops, was not wanting to do this. What this operator has to do, it has to tell the previous operator, hey, stop sending so much, I can't keep up, okay? So then the first one emits less, and then the second one is good to go, but because not as many records pile up. Of course, this just mitigates the problem to the first operator, because the stuff is coming in at the same speed. But this is, for example, happening at our application when, during these lunch times, when there's so many events and we can just not process them in real time. But then we don't want to blow our system, then we just introduce some latency. And therefore, we also need this persistent source, that the data is there somewhere, stored safely, and we can just say, okay, we don't read as fast now. There will be some latency, but we don't care. We just leave the records there, and when we can handle them, we'll read them in. So that's also a reason why you need this persistent source. And Flingstorm and Spark provide them, this back pressure mechanisms. And basically, it's buffers of limited size. So it's actually conceptually not a very complicated thing, but it's a very important thing. And in Spark, it's a little bit more difficult because you don't have these records one at a time. You have these batches, and what Spark does, it calculates how many records did I process in the last batch, how long did it take, and then is estimating of how many records it can read. And this is an important thing. You have to configure this, but it's usually then done out of the box. And what you might also take into consideration is back pressure between systems, but this is something that's very hard. I'm not going to cover it here, but maybe you want to have a back pressure of your whole processing pipeline or infrastructure, but this is something that's very hard. Okay, now the application looks like this. The operators know what they're doing. They tell the previous one, hey, slow down. Okay, last 2 ingredients are delivery guarantees, and we covered this a second ago. There's at most once, at least once, and exactly once. At most once is normally not so interesting because basically the application that writes everything into the trash bin is at most once. So what you normally want to have is at least once, meaning that every records get processed and processed at least once. And exactly once, of course, even in cases of failure, everything not necessarily gets processed exactly once, but all the state and all the output is like it was processed exactly once. And what we did in the past is you have one streaming application and one batch application at the same time. So this is called a Lambda architecture. And the batch process is running maybe like every 6 hours, processing the correct data, the absolute correct data. And the streaming is running in parallel, is giving you real-time results, but only average results or approximate results. So that way you could look into your streaming application, see, okay, it looks somewhere like this, but you would have to wait for the next batch program to really know what happened. But now we're a little bit further, and the streaming processes are very, very good at dealing with failures and giving you some data quality guarantees. So now I'm assuming a Kafka source, because that's the best you can actually do using a Kafka source, because it provides you with so many good guarantees. And in Kafka source you can get exactly once. In Flink you can also get exactly once. And in Storm, I just showed you, you can only get at least once. Even without failures, it could happen that records are duplicated. So Storm currently only has at least once. And while everybody's talking about exactly once and at least once, it's something like teenagers talking about sex. Because everybody who does big data talks about exactly once, and most of them don't really know what they're talking about. And only very few actually do it correctly. So there's a thing you should think about. Exactly once could be applied on state or on delivery. In the Flink example that I showed you earlier, we saw that the checkpoint was reread, and so the state was correct, even though there was a failure. But he said it correctly, the output was not correct. There was stuff output twice. So in this case, we did have exactly once state, but not exactly once delivery. And exactly once delivery is actually impossible in general. An application can't guarantee exactly once for all different types of sources and sinks. It is impossible to achieve it though, if you, for example, write into a database. If the Flink example that I showed you earlier would emit the record multiple times, but it was writing it into a database, then the stuff would just get updated and would be the same as if it was emitted once. So you can achieve exactly once delivery if you have idempotent sinks where the stuff just gets overridden. And HDFS, for example, the file system has a truncate method, so this can also have exactly once delivery. Truncate method meaning Flink then already tells HDFS, hey, I've written out too much. It's kind of a complicated thing, but then HDFS truncates the data, and then we do have it exactly once delivery. And Spark also has transactional updates into some sinks, so you can also get the exactly once delivery there. So finally, our application looks like this. You have some guarantees, and the stuff is working. And coming to the last important ingredient is monitoring, which is also quite straightforward. But I just want to stress here, don't underestimate monitoring. It's absolutely crucial to do it right and to spend time working on it, believe me. So you really want to know what's going on. So make sure you always know where the records are, where stuff gets processed and everything. And if you think about business metrics, that's not just only some byproduct that just comes out anyway. Because if you think about metrics, like the count, that's actually some kind of state. So you also want to think that the metrics should be correct, meaning they should have exactly one state. And so the frameworks provide you some metrics classes or some metrics things you can use, but they're usually not failure tolerant. So in the case of a failure, the metrics will just be down to 0. So last week we were actually looking that we have out of 80 million records duplicated 50,000 of them, and we're trying to figure out where, and we didn't know until we realized, oh, our metrics are not exactly once. The state of the metrics got set back to 0, so actually the output was correct. It was 800 million or 80 million and 50,000, just the metrics were incorrect. So I just want to stress here, make sure that you have some proper dashboards, you think about this exactly once metrics even, and then you know what's going on with your application. So finally, this application looks like this, and it works, and you're happy with it. You might be able to add some salt to this to make it a little bit more nice even. Our production tests, which sounds terrible at first, but it's a good idea because what you can do, you can inject some records into your production flow, maybe just 100 or something, and then in the end wait for these records and take a look. Did they even come out? Did they come out exactly the way I want it to be? And how long did it take them to come out? And then you always have some sense of how your application is really working and how much latency it actually introduces. So coming to a closing point here, what do you have to consider when you want to build an application like this? TLDA means too long, didn't listen. Hardware, you want to calculate generously, think about all these scenarios. load peaks, whatnot. Your stream processor should be, you should analyze really what you need. Take some time, do some proofs of concepts. Which features are really those that you need? Do you need exactly ones? Is at least once okay? What kind of algorithms do you want to run on this? So take your time on really thinking about which one of these is best for your case. All of these three that are presented to you, I think, are very good, but depending on what you want to do, one might be better than the other. So this is your job to figure out when you know your use case. State management, activate it, have some checkpointing. Oh, that's nesting. You don't want to have data loss and failure. You have to checkpoint the stuff. You want to have high availability. You don't want this master to fail and everything's gone. You want to have Zookeeper to take care of these single points of failures. You don't want to overload the system. Back pressure is the key word. Turn it on. It needs to be turned on. It's not there by default. Data quality, and know now what exactly once means, the difference between state and exactly once delivery. So if someone talking about exactly once, ask them, what are you actually talking about? Is it state or delivery? Monitoring, make sure you always know what's happening, and then you could do some production tests, see if everything's working, how long do the records actually take to get to the sync. I hope you learned something. Thank you for your patience, and if you have any questions, yeah, feel free to ask them. Thanks.